Hello, everyone. Welcome to NeurIPS 2020, the competition track. Today, we'll be talking about the SpaceNet 7 Multi-Temporal Urban Development Challenge. SpaceNet is a collaboration by a number of partners. It's run by CosmicWorks, but then partners also include Maxar, AWS, Capella Space, Topcoder, IEEE GRSS, the NGA, and Planet. I'm joined with a number of collaborators to give you this talk. I'm Anna Van from In-Q-Tel, but I'm joined by Grace from AWS, Todd from Maxar, Jake from Capella, Jesus from Planet, and Daniel from IQT. So we'll go through a number of pieces. We'll open it up, talk about SpaceNet, go through the data set, the metric, the winners, and then finally closing. So let's kick it off and talk about the SpaceNet 7 challenge. So this is a challenge that builds upon previous SpaceNets, but it features a deep time stack of planet imagery for the first time. It's the first SpaceNet challenge where we've actually had the temporal aspect being a key aspect here. And it's a hugely varied geographic data set, over 10 million building footprints over a long time span. And the public challenge portion was to precisely track urban development at the building footprint level. So not just pixels, but actual building footprints. And it ran in the autumn of 2020. On the right, you'll see here a GIF of one of the areas of interest, and you'll see the constructions going on over time. And again, the goal here is to track this. We'll get into the data set in much more detail in the next section. I'll turn over to Grace for a little bit more on the motivation behind this challenge.
Thanks, Adam. We were really excited to see the SpaceNet 7 challenge participation level and submissions, and looking forward to how the outputs will contribute to the work being done by organizations around the world that are exploring how machine learning applied to time series imagery to detect building change over time can make a difference, especially when combined with other data sets and analytics. There's such a potential to inform disaster and crisis use cases with this information. In thinking about the vast amount of open source satellite imagery available, building change detection is really a baseline need that can enable many types of analyses. Building footprints are often a proxy for population statistics, since this information is not readily available in many parts of the world. Understanding building change over time can provide insights into what areas are rapidly urbanizing, and this information can then be used as an input to models that estimate corresponding population increases and might help with prioritizing locations that could be in need of on-the-ground updates. Population levels are also a key input to disaster planning and response planning. Having up-to-date population information helps planners understand where the more heavily populated areas are and what infrastructure might be at risk. It can also be important in assessing changes in evacuation routes and thinking about how do increased or decreased population numbers impact resource needs and pre-provisioning of response and relief materials, or even shelter planning. Outside of disaster scenarios, understanding urbanization, changes in green space, and the potential impact on crop yields and water can flow into predictive models for analysis of humanitarian needs. What's most exciting is seeing how the outputs of SpaceNet 7 can open new innovations and new ways of thinking around using machine learning to identify emergent or ongoing trends in building change, especially as these could contribute to disasters and humanitarian crisis. Understanding these changes over time could have a significant impact on preparation, mitigation, and triaging responses and resource allocations to accelerate recovery. Back to you, Adam.
All right, thanks, Grace. So just a little more detail on the actual task here for SpaceNet 7, which is to take this stack of imagery on the left, where there's construction going on and change, and then precisely track the building footprints at each time step. Not only that, to assign a unique identifier, essentially an address for each building, and track that over time and have that persist. So this tracking of essentially addresses over time is a much more powerful result than either just pixels or just polygons. And this is the goal. It's rather ambitious, especially in medium resolution imagery. But as we'll show later, this is something that we saw great success in. So now we'll provide an introduction to SpaceNet, which is the overarching effort that brought SpaceNet 7. And for that, I'll turn it over to Jake and Todd.
Thanks, Adam. SpaceNet is a nonprofit LLC managed by Cosmic Works that's dedicated to accelerating open source artificial intelligence applied research for geospatial applications, specifically foundational mapping. The 2020 and 2021 partners for SpaceNet include the industry leaders and government organizations identified in the logos below. As we were thinking about creating SpaceNet, we wanted to make sure that the project was connected to solving real-world problems. As with any machine learning artificial intelligence application, it's important to understand what efficiencies can be gained with automation. In this example, we were really trying to focus on accelerated mapping, and the importance of this capability became apparent through the course of the project, particularly with natural disasters such as Hurricane Maria, when we looked at the time that it requires to manually create mapping layers post-disaster. So this is a great volunteer effort, and we were looking to try to identify ways in which this work could be accelerated with automated foundation map creation. There are four primary pillars of SpaceNet. We've focused on creating labeled training data sets for remote sensing geospatial data. To accelerate interest and innovation around the initiative, we've hosted 7 prize challenges on Top Coder with over $350,000 in total prizes, including 3,000 submissions worldwide. In addition, all the work part of this initiative has resulted in open source algorithms that have been released as a result of the challenges and can be used by the community to advance this work and research going forward. And we've established a number of performance metrics and detailed analyses that have been published and described as part of this effort for the evaluation. Some of the key characteristics that we identified early in the project were high quality labels. This was critical to model development, as well as creating structured label taxonomy. Availability of data was essential from the perspective of licensing and creating a model by which the data sets could be utilized for a variety of research before, during, and after the prize challenges. The data is hosted in an accessible way through the AWS cloud, and these data sets remain available and easily accessed in the cloud before, during, and after the challenge once again. And also, there's no request or pays model, so the data sets are no cost for the user to download. Lastly, we focused on interoperability around standards such as the cloud-optimized GeoTIFF, as well as the spatiotemporal asset catalog, structured in a way that the data sets could be used from challenge to challenge, as well as a variety of other research engagements. And now Jake is going to talk a little bit more in detail about each of these data sets.
Great, thanks, Todd. The first part of SpaceNet is ultimately the data or the satellite imagery. Our first 6 challenges focused on very high resolution satellite imagery, mainly in the electro-optical space, which is what this EO stands for. All of these cities, so we have 11 cities in total, have Maxar Worldview 2 or Worldview 3 satellite imagery associated with them. And we have 2 unique collects, the first of which is the off-nadir data in Atlanta, where a Worldview 2 satellite passed over Atlanta and collected 27 different shots over the same region in a few minute span. And we also have the Rotterdam data set, which features a combination of Maxar Worldview 2 satellite imagery, as well as Capella Space SAR data. On this next slide, you can also see the key component of another key component of SpaceNet, which is the foundational mapping labels. Ultimately, this includes both building footprints as well as road networks. In the high resolution portion of the data set, which spanned challenges 1 through 6, we had over 900,000 building footprint labels across 8 geographies. And then that was expanded significantly in SpaceNet 7, where we added over 10 million new labels across over 100 geographic areas using Planet's Dove satellite. Additionally, we have over 20,000 kilometers of road labels over 9 geographic areas. And this slide just highlights the distribution of our data with several thousand square kilometers of very high resolution satellite imagery, a great distribution of building footprint labels, as well as a significant amount of road labels over these different areas. So these were all of our challenges to date. SpaceNet started in 2016, and we have really strived to incrementally increase the complexity with each challenge over time. The first challenge focused on simple building footprint extraction in one city, Rio de Janeiro. We then moved on to building footprint detection in multiple cities, so Las Vegas, Paris, Khartoum, and Shanghai in SpaceNet 2. In SpaceNet 3, we moved towards automatically extracting road networks with AI algorithms in the same cities as SpaceNet 2. SpaceNet 4, as I previously mentioned, was the off-nadir challenge, where we investigated the effects of off-angle satellite imagery and how that can ultimately impact your AI algorithm's performance. SpaceNet 5, we returned to the roads challenge and really looked at if we could automatically extract routes and travel time. So how fast you on each of these road networks across 4 new cities. In SpaceNet 6, we added a new modality and had our first multimodal challenge, which featured a combination of electro-optical imagery and SAR data from Capella Space. SAR data being particularly important in a disaster response scenario due to its cloud penetrating capabilities. And finally, SpaceNet 7, which we're talking about now, has really been focused on change detection, which is still a holy grail and very difficult problem that we face in the remote sensing realm. And we believe that this challenge has really helped us to spur some further innovation in that field. All right, so the data set has been really impactful. We've had over 600 million hits to our S3 bucket, over 800 terabytes downloaded. After each challenge, we open source the prize-winning algorithms, and to date, we've open sourced over 36 unique algorithms for these different applications. We've had nearly 4,000 challenge submissions and a great array of international participation with 82 countries downloading the data set. With that, I'll turn it over to Jesus to walk us through the SpaceNet 7 data set.
Thank you, Jake. So let's dive into how we created the MUD dataset. All right, so let's start with high-level overview of this dataset. It consists of 100 time series of imagery. All these different time series are sampled at different geographical locations, so there is no overlap in space or in time. Each series has 24 images corresponding to different time points, and the size of these images is kind of standard. They are pretty much squares where every side is 1,000 pixels, corresponding to about 4 kilometers on the ground. So the area of every tile is about 16 to 18 square kilometers. And then for every image in this series, there's an associated label file with all the building footprints in that same image. All right, let's talk about the imagery and the source, where it comes from. And that is the Dove constellation of satellites. This constellation consists of 100 imaging satellites in low Earth orbit, about 500 kilometers in altitude. That is a little bit higher than the International Space Station. And all these satellites are distributed along the polar plane, forming like a ring, as you can see in this animation. These satellites are pointing straight down to the ground, and as they travel along the orbit, they scan the entire globe about once every single day. Each satellite, which is about the size of a shoebox, so pretty small, takes images in 4 different bands: visual RGB, red, green, blue, and band, with a pixel size that corresponds to roughly 4 meters on the ground. So these satellites, there are many satellites, and they take lots of image captures, about 2 million a day, and we usually call them scenes. And these scenes, however, are kind of hard to work with to analyze things. Their geographical footprint and timestamp is somewhat arbitrary, and most of them contain clouds, haze, and other atmospheric effects. So for this dataset, instead of using these raw scenes, we use the DOF basemaps, which is a reduction of this fire hose of scenes into a more standard spatial temporal grid. So to create a base map, typically the best scenes from every month are selected and merged together into mosaic tiles. And these mosaic tiles are then also spatially harmonized to make sure that the scenes blend together smoothly. And so the result is an image grid that is easy to work with and also nearly cloud-free. These base maps are global, and they exist for every month, building up an extensive archive that goes back several years. These are a great choice as a source imagery for the MUD dataset, since they provide, of course, clean imagery and also the temporal cadence that matches the typical timescales of urban developments. Another benefit of base maps is that they are created in a geographic projection and a tiling grid that makes it very easy to visualize in common web mapping tools. So now let's look into how we selected all the different dataset locations from these base maps. The main criterion was to show strong urban development over a time span of 2 years, corresponding to all of 2018 and all of 2019. We prioritize locations with urban developments that start with virgin land and end up with fully built buildings. So that was the most important thing. We did not target other construction processes like additional stories in an existing building or roofing work. Since all this stuff is really out of scope, we only consider change in actual building footprint. And this figure here in this slide really shows a good example of one of our time series. And there's a full neighborhood being built from scratch. And it is very nicely sampled at the monthly image cadence. Now, the second main criterion in the selection was to ensure a good geographical diversity across the globe. And in the end, all 6 continents are represented in the MUD dataset. Diversity is very important since buildings and generally the process of urban development can look very different across, around the world. And we want to make sure the models that are trained on this dataset are able to generalize well. Now we have spoken about the imagery. Now let's talk about the labels. Let's start with a definition of a label, of what a building is. We define a building as a static structure where a person could take shelter. So it is a pretty broad and general definition. With this definition, we have manually labeled individual building footprints in every image of the dataset. And these footprints are represented as simplified polygons in GeoJSON format. Every image has an associated GeoJSON file with all the labels in that image, of course. We also have defined just a single category of buildings, so with no minimum size. And here, large buildings are easy to identify, and it is possible to define clear outlines. However, the smallest buildings in the dataset are sometimes visually under-resolved, and they are also very abundant. So this obviously represents a unique challenge from a computer vision perspective. Common computer vision tasks generally deal with less objects per image and with larger object sizes. And here we have kind of the opposite scenario, as shown on the figure on the right. That is a comparison between our dataset in blue and the COCO, the common COCO dataset in red. And it's clear that our images have thousands of tiny objects, and also with the additional complexity of having to track them over time. So this makes this very special. Another unique aspect in our labeling strategy was to ensure that footprints are temporally consistent. And this is very important for time series modeling. What this means is that a footprint in consecutive images should stay the same unless the building structure has truly changed. Easy, but actually there are many image-to-image variation effects that could confuse an annotator. For example, things like varying shadows, color changes, seasonality changes, and so on. So during the annotation process, it was very important to visualize the entire time series at a time to really make sure that we were labeling changes when they really occurred. All right. Yeah, so a few slides ago, we discussed how this imagery are mostly cloud-free. And well, there are some rare cases where it's not. And we can find clouds, cloud shadows, haze, and even some image defects. These image areas affected by such conditions have been manually labeled into a mask layer called the unusable data mask. And these masks are created independently for each image. In the example in this slide, you can see a mask being applied to cloudy areas with a pretty aggressive buffer to make sure that all the cloudy bits and shadows are covered. Okay, so we are approaching the end of this section. I want to show some summary statistics on the dataset. Overall, it is a pretty unique one. I would highlight that it is probably the most geographically diverse dataset for urban development on satellite imagery. It is quite large, containing over 500,000 unique buildings and tracking them over 2 years. And so it has an unprecedented size, also diversity, and a it's very deep temporally as well. And all of these attributes make it great in order to open a green field for development of novel algorithms. Now, dense time series for object recognition at a global scale just became a reality, and this dataset can help develop the foundational techniques for future applications and scientific research. So, beyond the SpaceNet 7 challenge, we believe that this dataset will continue to have a lasting impact in the community. It is hosted in AWS and also open sourced with a pretty permissive license, free to use even for commercial applications. So we really hope that this dataset also continues to be augmented and transformed. For example, you can add and combine other imagery assets such as high-resolution optical, multispectral, or radar. Or alternatively, you can also just keep the imagery as is and create new labels on it. You can expand the existing building footprints or add different land cover classes. So overall, we are very excited to see the data fusion journey of this dataset over the next few years as more and more remote sensing assets become available to the community.
For this challenge, we need an evaluation metric to measure the performance of models in generating a set of proposed building footprints that correspond well to the ground truth building footprints, both in terms of their physical locations as expressed as polygons, but also in terms of using ID numbers to consistently track individual buildings from one time step to another. Now, since this is a time series problem, we could use evaluation metrics developed for tracking objects in film, things like the multiple object tracking accuracy, or MOTA metric. The issue with these kinds of metrics, however, for the most part, is that in this data set, we have many buildings that are there for much, if not all, of the interval and don't move around. And so a set of proposals could actually get a very good score on something like MOTA without capturing any of the dynamic change at all, which sort of negates the whole value of having the time series in the first place. So to solve this problem, we invented an evaluation metric of our own, the SpaceNet Change and Object Tracking, or SCOT metric. And the way this works is it is built out of two separate terms, a tracking term and a change detection term. The tracking term measures the model's ability to correctly use identification numbers, that is, to give each building an assigned identification number that is consistent with the previous time steps. So in short, the tracking term measures how well the model does at keeping track of what stays the same from time step to time step. The change detection term, on the other hand, measures the model's ability to correctly identify new construction, which in this data set is by far the most common kind of change. In other words, the change detection term measures the model's ability to perform on the things that do not stay the same from time step to time step. Now, both of these terms are actually kind of surprisingly similar in their calculation. They both start off with the SpaceNet metric, which was our original evaluation metric that we've used in previous building footprint challenges, where there was not a temporal component to the challenge. The SpaceNet metric looks for matches between proposal footprints and ground truth footprints, and then calculates an F1 score for those successful matches. To get from that to the tracking term, we introduced just one small tweak, which is that a match doesn't count if the identification numbers of the ground truth and proposal footprints contradict the identification numbers from previous time steps. On the other hand, for the change detection term, we start off with that original SpaceNet metric, except we simply ignore any proposal, ground truth, we simply ignore any footprint, ground truth or proposal, for which its ID number is not making its inaugural appearance. So with these seemingly small changes to an evaluation metric for a static situation, we can develop this two-term evaluation metric that really captures both aspects of a problem like this and looks at the full scope of what makes a successful solution in a task like the SpaceNet 7 challenge. So now to look at the most successful of the proposed models, I'll turn it back over to Adam.
All right, let's really get into the meat of it and the winners of SpaceNet 7. First of all, let's talk about the algorithmic baseline, which I think provides a little more context on the approach a lot of people took and some of the challenges incumbent in SpaceNet 7. So here's a schematic that the top row is time 0 and the bottom row is a different time. And what we're doing is we're inputting an image, running it through some segmentation model, getting out a mask, that's what we see here, extracting the polygons, and then assigning a unique identifier, right? This is key, this identifier. And then ideally, right, we're tracking those identifiers through time. So this is actually sample output from the baseline model, and you can see, you know, here is 171, and then later we still get 171. So doing a decent job of tracking this building identifier, which is essentially an address over time. But of course, it's not perfect. We also, again, remember we have real low resolution imagery. So at scale, the prediction mask is doing surprisingly well, but again, pulling out those buildings is the ultimate goal. And here's another overlay of this baseline model with the predictions. And again, it's tracking buildings between epochs with this resolution is quite tricky. In a lot of these, we're doing okay. So here's 401, and a later time, we're still seeing 401, but there are errors, of course. And hopefully the competitors will improve upon this. And turns out they did. So using the SCOT metric that we talked about earlier, the baseline model has a score of 17.1 out of 100, whereas we see the winning score more than doubles that with a score of 41, and pretty impressive performance given all the constraints here. And we see, you know, kind of most of the competitors using an efficient net, but the winner had a unique approach. And there's not a whole lot of difference here between the overall scores for the top 4. But one thing that was very interesting is that if you plot the score versus inference rate, there's a huge difference here. So up and to the right is better. So we see the baseline has a pretty low score, but it's pretty quick. And then you know, the second, third, and fourth competitors are all clustered right around here with pretty high performance, but pretty slow speed. The winner, though, was very fast model, and it was also the highest score as well. So this is what we'll go into in more detail, since in our estimation, this combination of inference rate and the high score makes it by far the most interesting. Just real quickly, the approach that was taken by these winners was to do a temporal collapse. And what that means is to kind of treat the time series kind of as a single step in a sense, and just look at all the buildings that appeared during the entire time. So on this bottom figure here, these are different epochs over the course of one data cube. And then on the left is this temporal collapse, where you're just looking at what appeared over the entirety. And if you do that, then you don't really have buildings move positions. That was what they implemented. And then they're assuming that the buildings have three options. They either are always there, they're never there, or they appear at certain time point. And they use this to figure out when the building originated. So remember, one of the key terms in the SCOT metric is figuring out when the building appeared. And so this kind of clever approach allowed them to greatly increase the change detection portion of SCOT by figuring out exactly what epoch a building appeared in. Here is a couple images of predictions. In this case, it's color coded by white is a true positive, blue is a false negative, and yellow is a false positive. So of course, there's lots of yellow and blue here, but a lot of white as well. And remember, given the resolution of 4 meters and the fact that most buildings are very, very small, there's a couple of pixels in size, doing a pretty good job. And of course, you can see there's construction going on. So from left, not a whole lot over here, and over here we see some more construction. But again, doing a pretty good job of prediction. If we zoom in, I think it's even more apparent than kind of how impressive this winning algorithm is. Here's a raw image of a test set. Here's the ground truth for that region in these nice squares. And here's the predictions, right? Again, the same color scale where the blue is a false negative, yellow is a false positive, but there's a lot of white here. So again, of course, the exact building outlines aren't perfect, not surprising given the scale, but if you're looking at building location and building size, doing an impressive job of pulling out these buildings when to the naked eye, it would be difficult, I think, for many people to label where buildings are in this case. So this brings us to the conclusion. We've had 7 challenges so far. We kind of went over that earlier, but just want to reiterate, been a lot of success. SpaceNet 7 was a new domain where we had the temporal aspect. And as we've seen, it was quite ambitious, but really impressive performance by the top competitors, and really excited to dive in this further as we further investigate all the things that they did to really improve the performance. So let's go a few of accomplishments of SpaceNets 1 through 7. We at this point have a massive repository of labeled data that spans the world, all 6 continents, both high resolution and medium resolution. And crucially, it's a permissive license. So this is something that's free to download. It can be used both academically and commercially. And so this has greatly increased uptake of this data set. We've brought together market competitors, Maxar, Planet, and Capella, have all been part of this, and which is pretty impressive, and academia and government into this formal partnership. We've engaged increasingly talented researchers to solve these difficult problems that are relevant to a lot of different areas. Disaster response is certainly one area that I think these efforts have really helped. For example, one of the perennial SpaceNet winners, Selim Sef, won the Facebook Deepfake Challenge, which was $1 million prize pool. So the point here is we've had very talented people compete in SpaceNet, and then the winner of SpaceNet 6 was placed in COCO historically. So we've had very, very good submissions to SpaceNet. Really happy with the quality there. And we've also provided open source code repositories for use by industry or academia. So the XView competition used SpaceNet code repositories for the baseline was an example of where this had impact. There's also been over 100 academic papers that use the SpaceNet data, which is pretty great. So the original goal, right, was SpaceNet name, right, was modeled off ImageNet, which is obviously a massively successful computer vision competition. And SpaceNet was obviously trying to do something similar for the geospatial remote sensing domain. And I think it's been largely successful, right? I mean, this is even acknowledged by Fei Li, who founded ImageNet, with a slide from back in 2017, and I think we've done a lot since then. All right, what does the future hold for SpaceNet? Well, Cosmic Works has managed all 7 challenges to date, but IQT Labs, which Cosmic Works is a part of, has decided to put resources elsewhere. We're looking to our SpaceNet partners to continue the initiative and carry forward. We are exploring options for setting up persistent scoring servers for SpaceNets 1 through 7, which will allow researchers to continue to use these data sets kind of as a benchmark and improve their algorithms. Regardless, data will remain available. There are many more research questions to be answered with this data set. So we really hope that people still find utility, keep using the data, and explore new challenges with this very rich and large data set. So I'll kind of leave it at that. We have a lot of information channels for people who want to learn more. The blog here in the bottom left is one to keep track of, especially as more analysis of SpaceNet 7 rolls out in the coming weeks. And we see kind of, again, more details on what was done with these impressive algorithms. And with that, really, we welcome questions on SpaceNet 7 or the future. And thank you all for your attendance.